Hi everyone, this is Krishna Malagapati. I'm working as a assistant professor in EEE department, St. Peter's Engineering College. Here in this video, I'm going to explain half-wave control rectifier with RL load. So we can use half-wave control rectifier with RL load for single phase feeding and three phase feeding also. So when we give the single phase supply to a half-wave control rectifier, we can call that as single phase half-wave control rectifier. If you are giving supply three phase, so that half-wave control rectifier will become three phase half-wave control rectifier. So based on the load that we are connecting, we are indicating here whether the load is R load, RL load or RLE load. So we'll see the circuit configuration. Okay. As I said, what do you mean by rectifier? The meaning of rectifier is rectifier is a power processing unit which is used to convert electrical energy, AC electrical energy into DC electrical energy. In other words, we can call that as it is a power electronics configuration which is used to convert AC electrical power into DC electrical power. It has a huge number of applications. So those we can say these are used in AC to DC conversions. These are used in AC to DC conversions and high voltage DC transmission purpose. So in case of nowadays what happened is to reduce the transmission losses, we are going to convert the AC energy which is going to be transmitted towards to the load from generating points in terms of DC values. For in that case also either sides we are using power converting stations. There the primary side means generating point side we are using a rectifier bank in power converting station. In that case we are using this type of devices a configuration. In case of secondary side means load side also we are going to use one power converting station. In that also we are using configurations. So these are the few things that we have to remember regarding to HVDC transmission, and it is also used in electrometallurgical process. It is also used in electrometallurgical process, and few more applications are magnetic power supplies. So in magnetic power supplies also this type of rectifiers are using, and electroplating process. In electroplating process also these rectifiers are using. Then when we see the battery charging means suppose if we want to charge the vehicle battery, so we can use the rectifier bank to convert that AC into DC. Thereby, we know that AC couldn't be stored, and whatever the AC is there must be utilized at that particular instant itself only. But when we convert that AC values into DC, we can able to store the DC values in batteries. After that, we can use that DC value. That application is there in electrical vehicles by putting some batteries to run the vehicle. Okay, and this is also used in speed control of DC drives. Speed control of DC drives also these type of rectifiers are using, and traction system. In traction systems also we are using rectifiers. So these are a few applications that we that there we are using rectifiers. We'll see. First one is single phase half wave control rectifier with R load. Okay. So I'm taking one circuit configuration here. It's very easy to draw and it's very easy to analyze, and it is very easy to understand also. Okay. So first I'm taking single phase AC supply. This is my single phase AC supply. After this I'm using one transformer. I tell you why I'm using here one transformer in the configuration. So this is my primary winding of transformer, and this is the secondary winding of transformer. Then, so my power processing unit, I am connecting one thyristor here. This is my thyristor, gate, anode, cathode, and voltage drop across thyristor is Vt. Okay, then we'll see. Then we are connecting one load here. This is my R load. This is my R load. It is very clear here. And voltage across load, you can say V0. Voltage across load is V0, and voltage across thyristor is Vt. I am calling this terminal is M, this terminal is N, right? Then this is my single phase 220 volt 50 hertz. So these are the ratings of single phase 50 hertz AC supply. So these all should be mentioned here. Don't do mistake while mentioning the ratings of single phase supply. This is very important here. This is my isolated transformer. Isolated transformer. I tell you what is the use of placing this transformer in the circuit configuration. Right? There I am using only one thyristor because it is halfway controlled. It is halfway controlled. Okay. Next we'll see the operation of this circuit. As we know, we are applying an alternating quantity. First we are applying positive half cycle. That is easier. This is the positive half cycle. This is the negative half cycle. One positive half cycle, one negative half cycle will become a complete cycle. And I am taking here in this diagram, in this waveforms, I am taking two cycles. So 0 to 2 pi is one cycle, 2 pi to 4 pi is another cycle. So with the help of that, we are going to analyze the entire circuit with the help of different waveforms. So what is this alpha? What is this alpha? Alpha is nothing but firing angle of the configuration. Please remember that firing angle is very important, right? And what do you mean by firing angle? It is an angle at an instant where the SR comes into conducting state. It is an instant where the SR is come into on state, conducting state. Means after giving the gate pulse to the gate terminal, then only this SR conducts. Until unless gate signal is not fired, this even though there exists forward voltage across the thyristor, doesn't conduct. It is there in forward blocking state. So that what we call that instant, what we call firing angle instant. That is indicated with alpha. Okay, please remember this alpha indicating firing angle. Firing angle means gate signal. The instant when the gate signal that we are applying to gate terminal, hence the SR comes to conducting state from its forward blocking state. Right? So now we are applying positive half cycle. Then I can say this is 220 volt. Primary winding of transformer having the 220 volt. Secondary winding is also carrying the 220 volt. Right? So I am calling this as an isolated transformer. So number of turns either sides of transformer are equal. N1 is equal to the N2. Please remember that. This is, I can say N1 is equal to N2, where N1 is the number of turns of primary winding of transformer, N2 is the number of turns of secondary winding of the transformer. Right? So when we apply the positive half cycle, you can say current is coming like this. Okay? Then here I mentioned that this will be plus, M will be plus, N will be minus. Then current is coming out like this. current is coming out like this, and through the load back to N, to the secondary winding. So what is the current path in this case? M, then thyristor, I am calling this thyristor is T. T is my thyristor. Then R load, this is R load. Then back to N, N to M. This is the path for current flowing in the circuit. If current is flowing in the circuit, I mentioned this current is I naught. Okay, so there is a voltage builds up, there is a voltage across the load, and after that alpha. Till positive half cycle is there in action, is there in the operation. So I am getting an output voltage from alpha to pi. During this, T1 is on. T1 is on. Sorry, T is on. Then look at this. This portion is clipped here. This portion is absent. Where is that portion? Means when you apply KVL to this circuit, when you apply to KVL to this circuit, this is the input supply. This is the voltage drop across thyristor, and this is the voltage across the load. So when you apply the KVL to this, input supply is equal to the voltage drop across thyristor and voltage across the load. Now what happened is, I got a maximum amount of voltage across the load, and this portion will be available across the thyristor. Now I am taking thyristor voltage over here. This entire portion is available here only. Thereafter, the voltage across thyristor is 0. What's the reason? What's the reason why that voltage drop across thyristor will be 0 when the thyristor is conducting? Thyristor conduction means it's going to be short circuited. It's going to be short circuited, allow the current to flow. As we know, the voltage across short circuit, it is minimum, and we can say that is the 0 value. That's why during on condition of thyristor, the voltage drop across the thyristor is going to be 0 till first positive half cycle come back to the 0 position at pi. This is the pi. So during this value, so that voltage drop across thyristor is 0, and this duration will get the output voltage. Right? It is very clear. Next, coming to negative half cycle. After pi 2 to pi, negative half cycle is going to be applied to the circuit. During that condition, during that timing, what happened? In that case, we have this will become minus, m become minus, n become plus, because it is negative half cycle. Now what happened is, current is coming out from M and back to M. This is the thing that must be happened in the circuit if the semiconductor device allows the current to flow through it. But what happened here? Look at this. Look at this very carefully. This operation is very important for negative half cycle of supply. So it is coming like this. Current is coming like this, entering into the load. Entering into the load, no issue up to this point. After this, what happened is, if the current is trying to flowing through the semiconductor device, as we know, one property of semiconductor thyristor is it is unidirectional device. It is unidirectional device. Otherwise, you can analyze this thyristor in some other way, that is, if the current is trying to move inside the thyristor towards the cathode terminal, through the cathode terminal, then what happened is, cathode is more positive than the anode. Cathode is more positive than the anode means what? It is in reverse bias condition. This reverse biased condition indicates what? Simply the device is going to be open circuited. Device is going to be open circuited. As we know, there is a voltage across open circuit, that the maximum voltage available and the zero currents are there for the open circuit, means it doesn't allow the current to flow. In this case, reverse bias condition, J1, J3 junctions are reverse biased, whereas J2 junction is in forward biased, and the depletion regions are increased inside the semiconductor device. That's why this doesn't allow the current flow in the reverse direction. We already seen them in static characteristics of thyristor. Right? During this one, no current flowing through the device, thereby there is no voltage drop across load. So during this condition, we do not get any output voltage. We are going to get the voltage across switch till 2 pi, till the next that negative half cycle comes to 0, right? And the other name for this type of converter is line commutated converter. Please remember this word, line commutated converter. Commutation is another topic. Commutation means to bring back the SCR from its on state to forward blocking state is nothing but commutation process. We are going to off the thyristor from its on condition. That is what we call commutation process. So here in this case, natural commutation takes place. Natural commutation in the sense the source itself making the thyristor off. Source itself making the thyristor off. Look at this. Positive half cycle is going to be reached back to 0 at pi. So at that instant, what happened is output voltage is going to be 0. Directly output voltage is going to be 0. So at the instant of negative half cycle starts. Negative half cycle starts means what? This way the current is trying to move opposite direction. Means what? The line side parameter, voltage or current, both are trying to bring back the anode voltage to below the holding current levels. Below the holding current levels, when we see in characteristics, VI characteristics of thyristor, less than the value of holding current indicates what? Forward blocking state of the device. So we can able to bring back the SCR from its on state to off state. That's what we call commutation process. It is line commutated rectifier circuit. Please remember this. And during this negative half cycle applied across the configuration, then there is no output voltage from pi to 2 pi. From pi to 2 pi, there is no voltage drop. Thereafter, what happened again? Pi 2 pi to alpha. There is 2 pi to alpha. Right. So next one is circuit turn off time. Look at this. From pi to 2 pi, there is no conduction, there is no current to flow in the circuit, thereby that what we call time duration when the current is not flowing through the circuit is nothing but circuit turn off time. From pi to 2 pi, there is no current flowing through the circuit, that's why this duration is called omega Tc. Omega Tc till alpha. Am I right? Till alpha, there is no current to flow in this one. So this one is nothing but, and here also same thing, the voltage drop is available across device. Then what happen again? For the next cycle, we are getting output till 3 pi. Thereafter, during this timing, what happened is the voltage drop across thyristor is 0. Then during negative half cycle, we are getting voltage like this. So these are the waveforms. See this? This is circuit turn off time. We can call that when we take its value, omega Tc is equal to T suffix C, it is circuit turn off time. It is upper limit is 2 pi, upper limit is 2 pi plus alpha minus pi. So this is 2 pi plus alpha minus pi. So how do we write this? This will be pi plus alpha. Pi plus alpha, and normal time is pi plus alpha upon omega. This is very important equation for every configuration, for every circuit. So in many competitive exams, they ask this type of questions. What is the circuit turn off time in case of single phase half wave control rectifier faded with single phase and with RL load? So when we connect the RL load for half wave control rectifier, what will be the circuit turn off time? They will give these some options, and we have to pick up the right option. Okay, that's very important. See, we'll see this is the source current. See the beauty of source current over here, and it is not same as the output current. See, output current is also follows the same nature of output voltage because the connected load is resistive load. Connected load is resistive load. Because of that, you can say V naught and I naught both are having the same shape, right? We'll see the input current, input source current, how it will be. Let us see. See, during 0 to alpha, no current is flowing. During 0 to alpha, no current is flowing. From alpha to pi, current is flowing. From alpha to pi, current is flowing. Look at this. Take it like this. Same as output voltage here. Then there is no current flowing. There is no current flowing to the load, source side during negative half cycle till this portion. Again, this one is having like this. Okay, this is same as these three. Means we can say I naught, Is, V naught are having the same shape, similar shape, right? So next we'll see the expressions, a few expressions that we have to see in case of single phase half wave control rectifier with R load. And we'll see the expressions. First we'll see, first one is average DC load voltage. Average DC load voltage. General equation for this one is V average is equal to 1 by T integral 0 to T Vs d omega t. This is a general equation. We are using this one for our configuration. That is 1 by 2 pi is my period of time, and the conduction takes place from alpha to pi only. From alpha to pi we are getting output voltage. That is a given input. And I am just replacing this Vs with its original value, that is Vm sin omega t d omega t. So Vs is replaced with its value Vm sin omega t d omega t. After doing simplification, this one using different trigonometry methods to solve this one, we will get one equation over here for average value of the load voltage. that is Vm by 2 pi, Vm by 2 pi 1 plus cos alpha, 1 plus cos alpha. This is average load voltage available for half wave control rectifier with R load. Okay, then average load current. Average load current will be, I can say that is 2 average load current AVG load current. Average load current I average is equal to, apply Ohm's law simply because it is a resistive load. So Vm upon 2 pi, I am writing R here itself, 1 plus cos alpha, 1 plus cos alpha. Simply just you apply the alpha value here, then you will get different values of that. Let us see one value. If we are placing alpha equal to 0 in this average equation, we will get V average equal to Vm by 2 pi, maximum value of output that we are going to get for alpha equal to 0. Suppose alpha that I have given maximum value pi, maximum variation is pi, thereby V average is equal to 0 value. Means output voltage is going to be varying from maximum value to the minimum value for the values of alpha, varying from 0 to pi. Right? We can write like this. So this is one of the important question that we will see in our competitive exams, that what is the range of firing angle in case of half-wave control rectifier with R load. So at that time we have to say alpha range, alpha varying from 0 to pi only, 0 to 180 degrees. Right? The third one we can see RMS load voltage. RMS load voltage, VRMS, you can call the VRMS is equal to simply 1 by 2 pi integral alpha 2 pi Vm square sin square omega t d omega t under root. I mean showing that with this. So when you simplify these things, you will get one final equation for RMS value. Okay. That equation is, I just rough and write the equation, please write. After doing simplification of this RMS load voltage equation, we are getting final equation is VRMS is equal to Vm of pi minus alpha 4 pi plus sin 2 alpha upon 8 pi under root. So root value that I am taking 1 by 2 is the final equation for RMS value of voltage, load voltage, that we can see in case of half control rectifier. And when we see the RMS value means very simple. Just you take that, this I am calling RMS load current. Why we are going to calculate RMS value? Because as I said, rectifier is nothing but it is a power electronic converter which is used to convert AC signal into DC signal. So we got the DC signal having the only average values. Why do we go for calculating the RMS values at the load side? So one more important point to be remember here is, apart from the fundamental value, means DC value, there are some harmonics. As I said, it is a semiconductor device, and it is going to be producing large number of harmonics in the system. Okay, so we have to calculate fundamental values and RMS values. That's why we are going to take the RMS calculation part for the output values. Then when we calculate IRMS, this is IRMS is nothing but, I'm just writing this one like this, Vm upon R simply, then pi minus alpha upon 4 pi plus sine 2 alpha upon 8 pi under root. So this is the RMS equation. Then we'll see next one, power delivered to the resistive load. Power delivered to the resistive load, that is RMS load voltage, RMS load current. RMS load voltage, RMS load current. Simply we are going to write that. PDC, power delivered to the load, is nothing but VRMS, IRMS. Right? Then 6.1, when we see this, input volt amperes. Input volt amperes, RMS source voltage. Input volt amperes, we can say yes. Power, yes. Apparent powers are indicated with letter yes. So input source voltage, we are calling that as simply Vs, right? Simply Vs and IRMS. Vs and IRMS. These two are same because look at this. This is I0 and this is IS. I0, IS, both are having the similar shape in case of resistive load. That's why we are taking directly this one. So with this, we can able to find out the input power factor. Input power factor. Input power factor, that is cos phi. Cos phi is nothing but power delivered to the load to the input volt amperes. Power delivered to the load to the input volt amperes. Then I am writing over here VRMS, IRMS upon Vs, IRMS. So IRMS being cancelled out. Then cos phi is nothing but VRMS upon Vs. So this is very important equation to be remembered for competitive exams. Okay. So with this some basics that we are going to discuss, and after that we can see form factor. Form factor can be calculated for this circuit. Then effective value of the AC component in load side. Effective value also to be calculated over here. And because of using transformer in the circuit, we have to calculate the transformer utilization factor. Transformer utilization factor. Transformer utilization factor is defined as the ratio of output power to the volt ampere rating of the transformer. Output power to the volt ampere rating of the power transformer. When we have that particular equations, it's very easy to find the TUF, transformer utilization factor. And finally, after getting these all the values, we should calculate rectifier efficiency. Rectifier efficiency also to calculate. And rectifier efficiency means efficiency in the sense, efficiency is defined as the ratio of output power to the input power. Once we know all the equations for that, we can easily calculate the efficiency of the rectifier. So with this class is completed. So in the next class we'll see single phase half wave control rectifier with RL load. Thank you.